Hello, and thank you for your attention in our work. My name is Nikita Kazarinov, and my colleague's name is Alexander Khvorov, and I'm going to talk about application of neural networks to prediction of impact strength of perforated targets. But firstly, I would like to talk about application of finite element method to simulation of impact in general. This is a very complicated task from the perspective of numerical methods, as it requires a lot of computational resources and application of complex material models and fracture models. Usually it involves contact. So there are a lot of errors in course of the simulation due to extreme deformations of the mesh. For example, on the left you can see a screenshot that was seen by practically everybody who worked with LS-DYNA trying to simulate impact. Negative volume error, which is due to excessive distortion of the elements. And on the right you can see a screenshot from ANSYS which tells us that there are problems with contact, so the so-called too much penetration problem. So let's suppose the following situation. We are trying to simulate a lot of impact problems, and these problems are characterized by some data. For example, target shape, projectile material, so boundary conditions, and projectile velocity. And for every data combination, we get the result using finite element method. For combination 1, we get the residual velocity value. For the next combination, we get the second value for the residual velocity, etc., up to data combination number n, for which we get the nth residual velocity. And we have all this data. We have this n-sized data set. But we want to get a new result for the new data combination n plus 1, and we want to get it fast. I mean that we want to use experience, and we want to use information that we already have about our problems. And we also would like to overcome possible numerical instabilities, meaning that we would like to be able to obtain the result for the data combination, which is hard to process using finite element method. So, is there any way to do this? Is there any algorithm to perform such task? This problem in this statement is very complicated, and it would be nice to narrow it and to simplify it a bit. Let's consider round PMMA targets. PMMA is polymethyl metaacrylate, which are hit by cylindrical projectile. We also consider we will consider two-dimensional statement of the problem, meaning that we apply axial symmetry here, since we suppose that our targets are round and that our projectile is also a cylinder. We suppose that all our problems are characterized by only one thing, a perforation pattern. So everything in our problems is similar except for the perforation pattern, which is effectively holes inside our target. But since we're applying axial symmetry, these holes are actually concentric canals inside the target. So we are going to study perforation of the targets with 3 resolutions. It's 2 by 12, 4 by 24, and 8 by 48. So our initial problem is reduced to the following one. We have n perforation patterns which are mapped to n residual velocities of the projectile. And we get the new perforation pattern n plus 1, and we want to get the result for it, and we want to get it fastly. So probably we have also some perforation patterns which can be processed by classic numerical methods like finite element method, and for these patterns we also want to get the result using the information we already have from these n-sized data set. Again, this problem is different for each perforation resolution, so they are not mixed. Um, firstly we need to get this n-size data set. How are we going to do this? We are going to perform finite elements simulations of the impact. We use several software pieces for this. We use ANSYS to generate mesh, LSDyno for the solution, and all this is organized and automated using Python scripts. In each problem we apply fixing of the target by this edge, and we use non-perforated layer to try to minimize problems with contact. For the fracture criterion, we use the incubation time fracture criterion. According to this criterion, surface from point x to x plus d is considered, and fracture occurs along the surface if the following inequality holds. Here d is the special fracture parameter which characterizes minimal fracture size, and this way sets the scale level of the fracture consideration. And tau here is the incubation time. According to this model, fracture is not an instant event, and it needs special preparatory processes to precede the macroscopic fracture. For these processes to occur, some time is required, and this time is the incubation time. In fact, these processes are of relaxation nature, and thus the incubation time is the characteristic time of the relaxation processes which precede fracture at a chosen scale level. In our case, we consider fracture inside the element, and we consider several orientations of the area inside the element using these angles. So this fracture criterion can be easily integrated into finite element code, since we can choose the mesh size equaling d and to consider the stresses inside the element. We need to calibrate our model using some experimental data. So to calibrate the model, we use data we obtained in our previous work, where we measured experimentally the residual velocity of the projectile penetrating the PMMA targets, and we performed the calibration using the non-perforated model. So we feed this, we adjust the parameters, feed the experimental data. This graph shows dependence of the residual impactor velocity on the initial impactor velocity, and then we use this model and material data and model parameters to perform all the rest simulations, which include the perforated targets. Finally, you can see here how the targets with different perforation resolutions perform during the impact test. On the left, you see the pre-meshed cells, which are used as bricks, as Lego bricks to assemble our model. And on the right, you see the performance of some random perforation patterns of different perforation resolutions. So, finally, we know how to get our data sets consisting of finite element method results. But now we need to construct an algorithm that would study all this data and will be able to make predictions for the new data pieces that are not presented in our data set. Well, for this we are going to use the neural network. The neural network should be considered as a pretty complicated function that maps our input, which is in our case the perforation pattern, to the result, which is the residual velocity of the projectile. So our perforation pattern is encoded using a matrix, which is then put to the neural network, either to make a prediction or to train it. For the efficiency assessment, we use two metrics. The First metric is the so-called R2 metric, which essentially shows the advantage of our neural network model over prediction using some data averaging. And the second metric is used for the problems with binary results. By binary results, I mean problems with where you can say yes or no, or something left to right, zero or unity, something like this. And this is measured simply by dividing the number of successful predictions by total number of predictions. So if the accuracy metric is around 0.5, then the model is guessing. It's like tossing a coin. And this should be considered as a bad result. It's a bad model. For our research, we used two architectures of the neural networks. The first one is the fully connected network, and the second one is the convolutional network. The main difference between them is that the convolutional network searches for specific patterns inside our input using special filters. We use a 3x3 filter window here for all the problems. And we had very high hopes for especially convolutional neural network because they are known to be very successful for the problems of the image processing. And probably you see that our problem reminds a lot resembles a lot the image processing problem, since the perforation pattern can be considered as image. Okay, we tested a lot of them, and the conv stands here for convolution, and those numbers they encode the number of intermediate layers with 20 filters inside each layer. And here also we this way we encode a fully connected network with two intermediate layers with 20 neurons in each layer. So we use this type of notation. Let's turn to the first portion of the results we got. The first results I'm showing is the result for the test problem we used to test our approach generally. Here we used the deflection of the plate, static deflection of the plate with perforation, and we tried to guess, is it going to deflect to the right or to the left due to perforation. So for the low resolution perforation patterns, you can actually say if it's going to be left or right by just looking at this pattern. But for high resolution patterns, it can be tricky, and calculations are needed. Surprisingly, convolutional neural networks completely failed for this task. And fully connected networks worked really, really well. Even the simplest fully connected network, which is a linear regression model. And the failure of the convolutional neural networks probably can be easily explained by the fact that these types of neural networks do not sense the location or general location of the cells. It looks for specific local patterns, but particularly for this problem, we need to see the balance between holes and solid cells in the left and in the right side of the plate. And the convolutional neural network just can't do it. It looks locally in our sample, and it doesn't see the whole perspective of the sample. So this is how mechanical statement of the problem influences the choice of the architecture of the neural network. This is the first time when we see it. Let's move to the results for the main problem, for the impact problem. You see here a table with results for various combinations of intermediate layers and with different amounts of neurons and filters inside those layers. And we selected probably the optimal from our point of view architectures. This is the fully connected network with 2 layers and a convolutional network with 4 intermediate convolutional layers. For this problem, it is obvious that for the higher is the resolution of the perforation, the more data we need to train our network efficiently. For example, for the largest problem, for 8 by 48 with resolution, we need over 100,000 problems to be solved. But it is interesting to note here that the accuracy for the high velocity problem, for the problem with high velocity of the projectile, is much higher comparing to the lower velocity problem. You see here on this graph, the blue color depicts error for the test problems. Here, for each problem, we have 1,000 tests, and we test 4 problem sets. For 3 of them are 95 meters per second, the velocity of the projectile, and 3 different perforation resolutions, and the 4th one is the 200 meters per second problem. And for this particular high velocity problem, the error is much lower. This is an interesting fact, and probably it's due to the fact that for the high velocity, it is not that important how holes and how perforation is distributed exactly inside the target. The more important is whether there are holes beneath the contact spot or there are only solid cells. So this way, a lot of combinations are just merged for the neural network, and she doesn't see the difference between them. And this way, the problem is for the prediction problem is simplified for the neural network, and the complexity drops. So the error becomes smaller. And you can also see that some of the points are below the dashed line, which indicates the level of protection of the residual velocity of the solid target, meaning that some of the perforation patterns give us better results than the solid one. This is valid for lower velocity projectile. For the high velocity projectile, it's not valid. So for the low velocity, we can find some perforation patterns that provide us better resistance to impact, which is very interesting and which will be used further for the optimization purposes. So we noticed this, and we constructed a simple genetic algorithm that would use convolutional neural network as at the evaluation stage. The genetic algorithm just selects some candidates, merges them, performs mutation procedure, mixes somehow features from these candidates, and then checks their, let's call them children. So if the child is successful, then it decides that we should keep this feature for further generations, and this way the whole population of optimized structures, in our case optimized perforation patterns, evolves, and finally we get some result which satisfies us. So normally at the evaluation stage we would use just normal computation using finite element method, but here we try to use convolutional neural network for faster evaluation stage, just to save our time, and it worked. The accuracy, the efficiency of our neural networks was sufficient to build some optimized perforation patterns. And for this particular pattern, this particular perforation pattern manages to reduce the residual velocity of the projectile by 28%, from 50 meters per second down to 36 meters per second. This is done by splitting this single vertical crack for the solid target into 2 cracks, 2 inclined cracks, which generate a big fragment which consumes momentum from the projectile and slows it down. This is the common feature for all these optimized projectile or perforation patterns, just to generate a large piece that would consume our momentum from the projectile. And finally, we turn to the results for the failed calculation. calculations. As we decided in the beginning, we would like our algorithm to predict the results for the problematic cases. And for our problem, we had such cases. Some perforation patterns resulted into abrupt termination of the calculation due to heavily distorted elements beneath the projectile. You see such situation right here. For the lower velocity, it was not such a problem because only 200 out of 25,000 configurations failed, but for the high velocity, it became a problem since 7,800 failed out of 48,000 problems. Firstly, what we did, we tried to predict, we tried to use our neural networks. For this case, that was the convolutional neural network with 4 layers. We tried to use it to predict if the particular configuration will lead to failure of the solver. And we couldn't do it. It failed. We just couldn't get the accuracy of this prediction higher than 50 or 60%, which is again guessing. And from the prediction perspective, it is not good at all. But this way, we can say that these problematic configurations do not form a subclass inside the dataset. They actually share features with the rest of the dataset, which are normal configurations. This way, we can be sure that we should expect the same level of accuracy for the bad configurations, just as we get it for the normal ones, because they are the same from the point of view of the neural network. They are not, they do not form any special group. They do not obtain any special feature. The fail or not fail is just random from the point of view of the neural network, and this is very, very beneficial for us. For some of the bad configurations, we could actually overcome these computational problems by a reduction of the time step, and we did it. For some of them it worked. This way we could check accuracy of our predictions using neural networks, and the accuracy was pretty high. The R2 score was 0.96 for the high velocity problem. So this is really, really good. And for this, by the way, for this particular configuration, we couldn't resolve this problem using the time step reduction. So we used the neural network to make a prediction, and here is the prediction done by our model. So the conclusions. We used a very, very simple problem of the perforated targets to show that the neural networks can be used to predict FEM results with high accuracy, but without complicated computations, which require a lot of resources and time, etc., etc. And yes, we do not need licenses for these ANSYS and the LSDyno to perform these computations. Of course, we needed to build a data set, but after you do it, all next computations are free for you. Maybe it's good for web applications where a lot of users can apply for a computation simultaneously, and you can provide them results, maybe less accurate, but instantly. So we also found that model architecture depends heavily on the physics of the problem. It was shown by the static problem and by the fact that it's the high accuracy for the high velocity problems. So, and we also show that the neural networks can be used to predict results for problematic cases where FEM or any other method fails. It all works for our simple problem, or probably toy problem, theoretical one. But again, I come back to this figure where I show that the real problems can be described by multiple data, by projectile velocity, etc., etc. And we actually don't know if this approach will work here, but it's worth trying. So thank you for your attention.